Welcome back to Folzor, and in this video we are going to look at how can we make the 4004 microprocessor from 1971. This was a revolutionary processor in the CPU market, the first microprocessor ever be sold, ever. It launched Intel's biggest campaign of selling microprocessors, because before that they were just a RAM company. All they did was make RAM chips, but then they swapped to microprocessors because of an inflection point in the CPU and silicon marketplace back in the 1970s. So we're going to look at actually some really detailed circuitry behind the 4004, probably more detailed than you really ever want to know. But that's the whole point of this channel, is to really dive into those small details. So the circuit doesn't work actually. I'm sorry about that. It took me a long time to really understand how the 4004 worked, because it has a few quirks that we're going to explain in the next part after this little introduction. But I do understand how it works now, and so I'm going to present this knowledge to you, because if you look up how the 4004 works, you'll see the same kind of basic outline, which is good, but then you'll see really like the transistors circuitry, which is kind of hard to understand. So I'm going to explain it all. As always, Discord's going to be in the description, my shop's going to be in the description, all my other links are going to be in the description in case you want to check it out and join our little community of computer nerds, you can say, that like building computers. But let's get into the facts. Welcome back in the simulation, and we are going to look at the Intel 4004 microprocessor, the first one on the market, how it works. I'm going to explain how it works, the other parts in the series too, because it wasn't just the 404. But for me to get started with this, the simulation doesn't work. Okay, look, I know you're sad. I know I've made a lot of simulations that do work. It might look like it's working, but it doesn't. And that's because this thing is it's really glitching on me right now. It's very glitchy. It doesn't really seem to want to work. So that is kind of sad, because we can't get our system to function. But I did make enough of it so I can easily explain how this works. Okay, so Intel 4004 was used for this BusyCom calculator. So it was a 4-bit calculator. It can do basic functions like add, subtract, multiply, divide numbers. Really, that's all it can do. It wasn't a scientific calculator. It was used for accounting. So that's really all you need to do, especially with money. And first things first, we're going to look at how this thing really worked. So this is the little Wikipedia page right here that I just found. And this is a good schematic of what was really inside this 4004. So first thing, let's start at the bottom. We have 2 clock signals, which we just cannot simulate that at all. We just straight up cannot simulate that. And they're going in, and the clock signals are like this because they activate different stages of the machine. Another thing too is, look at this data bus. It's bidirectional. That means it's sending data and receiving data on the same bus, which is kind of hard for us to simulate that too, but not necessarily impossible. Besides this, it is an accumulator CPU. So we have our accumulator, and then our little temporary register, our flags, and then our decimal adjust circuit, and so on. So that's what we have in our thing. Also, we have RAM, so we can control which RAM module is activated, and other sorts of outputs. So let's look at this thing. So first, data is going to be sent onto our data bus from whatever RAM source or ROM source we have. And then it's going to go into the instruction register. It's going to decode it and then send it to our controls, and it's going to control the data, so on. But everything's in 4-bit. So let's see if I can kind of explain this part of it, going back to our simulation. So an instruction cycle is about 8 clock pulses, you can say. So in the instruction cycle, it needs to fetch, decode, and execute the 3 main components of the CPU. It's doing this all with 4 bits. And so the program counter is a 12-bit program counter, so it can access at least 4 kilobytes of storage. But 12 is obviously a lot bigger than 4, so it needs to save its data in 3 clock pulses. So it takes 3 clock pulses or 3 shifts of a shift register to receive all that data. Yeah, and then it's going to send out the receive the data of the, or send out the data, send out the data of the ROM, and then the ROM's going to give back the data that the opcodes have. So it also has 2 opcodes. Some have 1 opcode and some have 2. So, but opcodes are all the opcodes are 8 bits. So if it has 1 opcode, it's still 8 bits. It still needs to send it in 2 waves, okay? And you can kind of see that, what I mean, if you look at our control register. We have these 2 registers right here. This one's the opcode and this one's the operand. Some of them have 2 opcodes. So, for example, let's say we want to jump to, I don't know, byte 1000 in ROM. That's going to take 2 opcodes. So we're going to have to send the first opcode, which is jump, and then the next 3 4-bit spots are going to represent, hey, we want to jump to ROM 1000. My simulation doesn't even account for that because the timing is incredible. That's why there's 2 clocks, because of how hard this timing really is to pull off. So let's go back to our little photo real quick. So that's how that's going to work. Take 3 clock signals. So, and instructions are 8 clock signals. So there's 3 already. It can decode it pretty much instantly. And then the rest of the clock signals are used to do whatever the opcode wants it to do, essentially. And that's how it works. We have 16 registers. The registers can be paired together to make this 4-bit register, which is kind of nice. And then another weird thing is the program counter and then the ALU. And that's pretty much it of all the weirdness, I would say, apart from the CPU. So the program counter actually does work pretty well, I'm going to say, with our simulation. So we're going to open that up real quick. And look at this. I would say this is pretty accurate. It's definitely not 100% the way the logic is supposed to be used, but it gives a very similar result. So the data can enter here if we want to jump. So we can enter the data here, we can shift it through the shift registers, and then we can send it onto our bus. So we can jump to a certain place in the ROM. But we also have these 4 different 3 like register cells, you can say. And again, we're going to go back to our little thing real quick, and that's their stacks. So we actually have 4 stacks. And this one shows 3 stacks, but we also have the program counter at the top. So we have 4 stacks, okay? And then we have our stack pointer, which is at the top. So that shows which stack is being currently read right now, which stack is counted as number 1, essentially. So we're going through all these stacks like this, and then we can shift the stacks with this button right here, and then we can either increment it or decrease it. So if it's high, we decrease the stacks. If it's low, we can increment the stacks. Okay, and then we can save it right here. So you see, once we save it, it increments by 1, just like a program counter would. And our jump features are all the way at the bottom right here. So once we increment it by 1, now we need to output this on a 4-bit bus, and we do this with these shift registers right here. So first of all, we're going to save it. We're going to save the program. We're going to turn the switch on so it can switch from the multiplexers. And then we're going to shift. And then we shift it out like that, just like that. And then we can turn the tri-state off so it can all fit on 1 bus. So that's essentially how this works. So let's say that we can save kind of jump locations. So, which is kind of interesting because you might think, well, can't we just jump to the code with a jump command? And you kind of could. So I'm not too sure what the stacks were used for, just like this, but I'm sure there was a reason for it. And I guess it just allowed for biconditional branching a little bit easier or differently. But from my understanding of the 4004, this is kind of what the stack program counter would have behaved like. It definitely wouldn't have acted like this with this half adder array right here to add the numbers. But this is 100% what it would have behaved like, at least. And now let's go to our ALU, wherever it is. So the 4004 kind of added numbers a little bit differently. A normal computer would just add the binary numbers together, but this was used for calculators. So it was heavily designed towards a calculator. So a 4-bit number can represent numbers from 0 to 15. And in decimal, all the numbers we really care about is 0 to 9. So each 4-bit number is going to represent a place value of our base 10 system in a calculation. So 389 wouldn't be a 9-bit binary number. It would literally be 3, 8, and 9, all with 4 bits. And they just kind of shifted together with shift registers, you can say. And so that's essentially how this would behave. Okay, so let's make a number up. I'm going to write this down too. Let's make 3 87 plus 199. So those are the two numbers we're going to add up right now. So first we're going to add 7 plus 9. Okay. And then we're going to shift this real quick too, once I make the shift. Okay, so we shifted it. And now we're going to save the carry. Now the next digit in 387 plus 199 is 9 plus 8, okay, with the carry high. So now we're going to shift this out. The carry is still high, so we're still going to keep it high. And now we're going to go the last digit, which is 3 plus 1. And we're going to shift. And now we get our answer, which is 586. And to check it, I'm going to use this calculator, which is 586. So it works. And this is exactly how the 4004 would do it. It would calculate the numbers and just shift it bit by bit, which is genius because this takes significantly less transistors to do. It just takes a little bit more time. But since the 4004 was never meant to display on a monitor, which uses millions of pixels, it was only meant to display on a piece of paper, which acted like a 7-segment display. And this is beautiful for a 7-segment display computer because all you can display on it can be represented with a single 4-bit number, and you just shift it per calculation. So that is how it would do math, which is one of the main features or the main things that differentiates it between other CPUs. It's this program counter, it's the way it does math, and the weird clock that we kind of see. So let me see if I can pull it up again real quick. So that's exactly how it did it all. And everything had to be shifted in and out, which again made a timing nightmare. And so that's basically it. And the double dabble program that you might have seen me make, the double dabble circuit, works essentially the same way, except it doesn't do it per clock pulse. It actually does it all at once, which can save you a few clock signals. But I mean, just look at this. This is just so much easier on transistor count and simplicity. So if you want to make a 64-bit number, you could essentially just clock this a few times and kind of have it shift by itself and load it in different 4-bit chunks. But that is essentially it about the 4004. I'm going to go over a few more parts real quick. So the 4001 is the ROM. This is the memory of the series. The 4003 was the shift registers. So it needed a way to store the data, and it would use shift registers, and that was pretty much the whole 4003. And the 4002, which is not on here, is the RAM. And the reason I don't like making RAM in the simulation is because it takes a lot of CPU power from my laptop to actually run and maintain the RAM, because there's just so many elements happening in a single RAM chip. But that is how the 4004 would have behaved. And it was used for the BusyCom, which is this right here. So now let's go over the operands real quick, and then we're gonna pretty much be done with this. So here's a better representation of our opcodes too. And this is the exact order that they appeared in on the normal instruction set. So we have 0, 0, no option. Then we have 1 is going to be jump conditional. Okay, so we're going to jump if the 0 flag or the carry flag is high, depending on which one. We have fetch, so we're going to fetch some data. We're going to fetch the data, fetch the address. We're going to add or send an address to the RAM or ROM port is 3. Jump unconditional, jump no matter what. Jump subroot, which is jump for the different sections of our thing. Increment the register. Increment but skip if it's 0. So if the register is 0, we're going to skip it. We're going to add is 4, subtract is 5. Add is 8, subtract is 9. 10 is we're going to load data to the accumulator. And then we have 11 is we're going to exchange data between the register and the accumulator. 12 is we're going to branch. 13 we're just going to load immediately to the accumulator. And then we have 14 is our IO. And then 15 is the most interesting opcode of them all. It's the accumulator group, or the math group opcode. So if you have 15, if the opcode is 15, and then the next operand is 0, 0, we're going to clear the accumulator. If it's 15-1, we're going to clear the carry. 15-2, we're going to increment the accumulator. 15-3, we're going to complement the carry, so basically swap, inverse the carry. 15-5, we're going to shift it to the left. 15-6, we're going to shift it to the right. 15-7, we're going to do something to it. 15-8, we're going to convert the decimal, or the binary to decimal, which we can turn it on or off depending on what we really want the CPU to accomplish, since it's a general purpose CPU. And so 9, so on the accumulator group 9, it's transfer, carry, subtract. So we want to subtract with the carry on. 10 is going to be set the carry, so you can set the carry high. Then 11 is going to be a decimal adjust, so we can actually put decimal points in our answer by just kind of shifting the numbers over, because adding 2.1 to 1.1 is the same as adding 21 plus 11, but then we just shift the decimal over. Same thing. 12 is keyboard. So if the accumulator group is on and 12 is on, we're going to take in a keyboard input. And then 13 is command line, and then the next one, 4 is going to be complement the accumulator. So I kind of skipped that one, but that's essentially all of them that are part of the accumulator group. And it's 46 instructions, and as you can see, it's really operated towards this calculator. It's really good at being a basic calculator. But that's essentially all it was made for, and it can do a few other things too. But again, the instructions were about 8 to 9. The first 3 were the addresses of the ROM, and then we have the decode, and then the next 4 was the execution part of the thing. So that's essentially how the 4004 worked. I just want to give this little explanation just so we can really appreciate, because this was all made in 1971, and it actually took me an incredible amount of time to really understand how it worked, and I spent an incredible amount of time on just fooling with this. Even though it still doesn't work, it took me forever to really build the program counter and the control unit and the accumulator. Like, the accumulator works. It can do most of the functions, or most of the opcodes part of the accumulator group, And that's with this right here. This is the accumulator group. So if this is on and this receives a signal, then we kind of operate it towards what we want to do. And that is, we can, you know, clear the accumulator, of course. We can increment it by 1. We can decrease it. We can shift it, which the shift took an incredible amount of time right here because it shifts with the carry, which is such a minor detail, but it makes all the difference in the actual calculation. And then, of course, we have our 0 flag, so we can know if is the accumulator 0, and if not, we can kind of shift it through. But yeah, that is how it works. I will put this up on the shop. Like I said, the circuit doesn't really work, so if you do want to buy it, I'll be happy. It'll be on there for very, very cheap. But if you do want to figure it out and try to fool with it, or try to just play around with the accumulator or the program counter, you're more than welcome to. Like I said, it'll be pretty cheap on my shop. But that is it for this. Next week, we're going to design our own 8-bit CPU, and we're going to get it ordered. Yes, so this is what I've been waiting for a long time. I've been putting lots of hours in this week. I learned a lot about it. I'm still not really set on a final design yet for the CPU, since I wanted to do so many different abilities, but I'm very excited to present this to y'all next week. But thank you